talk about array processing. So if we have array of multiple sensors, M sensors, and this is a very simple model. So we have something like that, yt equals to. So in the time domain, we can also work with convolution. Okay, so ymt will be gmt convolved with the desired source plus vmt. So this is the model in the time domain. And we can make some assumptions about the transfer function, the impulse response from the source to each of the sensor. And we have M sensors. In the frequency domain, we have ymf equals to g mf xf plus v mf. So in the frequency domain, we write it like this, but in practice, we don't work with Fourier transform. We work with windowed Fourier transform. So in the STFT, we work with windows, and then we can give like time frequency beams. So in the slides, I write it in some way, but in the literature, sometimes we write it like this. So each sensor has two indices, time and frequency, like this. And the time, so sometimes instead of time, we call it like R multiplied with capital R. So this will be the index of the time window. But we can also put here time, but this time is different than this time. Okay, because here it's the samples. So with the interval, it's the sampling interval. Here, T is the index of the window. And then we have some jump or this difference, hop, we call it hop, between windows. So this is the index of the position of the time window. So here we get like, for each frequency, we get samples. Okay, so even if we fix the frequency, we get samples along the time or the index of the window. And then we can also write it either something like that. So suppose that the transfer function from the source to each of the sensors is constant, so it doesn't depend on time. But sometimes there are movements. The source moves, maybe the array moves. For example, wearable arrays. So if we put the arrays on a person, like glasses, smart glasses, or we put some sensors to measure something on the body, or outside. So many times, either the source moves and we need to track it, and maybe the array moves. So practical situations involve more complicated transfer functions. So that's why we don't work in the frequency domain. We work in the short time Fourier transform domain, or other transform are related to window transformed. So short time Fourier transform is very useful because for each window, we can choose the length of the window, and it approximates. Instead of working with joint diagonalization, we work with STFT, which is a good approximation depending on what type of signals you have, okay? And then how do we write it in the STFT domain? So sometimes people write it with a multiplication. So they say for each time frequency domain, we multiply it with a transfer function like this. G, M, T, F. So the fact that we use for each window a different transfer function, it means that we allow the transfer function to change. And of course, we need to track these changes. But I'm talking about the model. I want you to see that there are different models for working with array processing. Okay? So this, many times, we choose multiplication with the time frequency bin of the source plus V, the noise in the time frequency bin. Okay, and of course you need also models for the noise. Okay, so sometimes it's useful to split just like we talked yesterday or day before yesterday. So we split the noise into at least two components. One component which is correlated with the noise at the reference signal, and the other component is the remaining noise components. And it's also possible to do additional things. Okay, but I try to simplify things, the basics. Okay. Here we make a very important assumption. Okay? So when we come from the time domain to the time frequency domain, and we write it like this, we made a very important assumption that you need to be aware of. What is the assumption? The assumption is, actually there are two assumptions. First, that the length of the extent of this impulse response is sufficiently short and smooth with respect to the window of the short-time Fourier transform. That's why we move here from convolution to what we call MTF. MTF is multiplicative transfer function. And this is a very important thing to notice. Okay? So we assume that the impulse response is short, sufficiently short, relative to the length of the window of the short-time Fourier transform. So what we said that sometimes you don't want to work with long window in the STFT, because you want to work with the window such that the signals can be approximated as stationary during that window. For example, for speech signals, we work roughly with 20, 30, 40, 50, and maybe sometimes 60 milliseconds. But the impulse response in the room, for example here, when I speak, if you put a microphone on where you listen to my speech, the impulse response in this room can be hundreds of milliseconds. So it's much longer than the length of the window. Of course, we can take longer window of the STFT, but this has a very, big disadvantages, because then during that window we cannot discriminate or identify different phonemes or different parts of the speech, because during that window the signal is non-stationary, is changing during hundreds of milliseconds. So what do we do? Okay? So instead of coming from here to here, you see, we need to do something else. YMTF. We can write it as GMTF convolution, and here the convolution is just along the time. Okay? So it's convolution in time with XTF plus VMTF, which means that we can write it as, see, sum over tau GMTF tau f xt minus tau f plus vmtf. So this will be the model, which is very important. You see, it's a convolution in the time axis while f is fixed. So we don't use data from different frequencies. So it's like convolution. So this is called convolutive transfer function in the STFT domain. So it's convolutive because we use convolution. So what you can do is to take, even if you work in the STFT domain, you can process signals for each frequency, and then we need to take some windows, okay, additional windows. And we can take for each, so for each sensor, we can take L windows, such that we can approximate this convolution. And then we concatenate these L windows of M sensors. So we get a vector. So here, remember in the time domain, we worked with a vector. Okay, so we defined a vector of length ml by 1. So this is the vector of measurement. Why? Because we took L samples from each sensor and we concatenate them of all the sensors, and we work with vectors of length ml in the time domain, multi-channel. Okay, we work with multi-channel. This is in the time domain. In the frequency domain, with this, okay, we worked with vectors of length m. Okay? So these vectors, we worked with this, and the filters also. The filters here, it's length ml. So we work with filters of length ml. Here we worked with filters of length m. And when we moved, we talked about extension or implementation in the STFT domain. So if we use the MTF approximation, the multiplicative transfer function approximation, this is approximation of this model. Generally, it's not correct mathematically. It's an approximation which can be satisfied when the impulse response is short compared to the window. So when we have short impulse responses, so we have just a few reflections. We don't have many reflections and reverberation. So under the MTF approximation, we can also work similarly to the Fourier transform. So we can work with filters of length m. So we work with filters of length m for each frequency. Okay? And how many frequencies do we have? So if the length of the window is L in the STFT domain, if we have L, the length of the window is L, so we have here L, also here, if we have L frequencies, so we have L filters of length M. You see all of that connection? Very nice. So here we worked with long filters of length ML in the frequency domain and in the STFT domain with the MTF approximation, which is very similar. We work with L filters of length M. So the problem, or all the derivations of the optimal filters is much simpler, because it's much simpler to work with smaller matrices of M by M. The coherence function, the coherence matrices are much smaller, of size M by M. So we split the problem of finding the optimal filter of length ml into L problems of finding filters of length m. Let's do this, okay, either in the Fourier transform or the STFT. That's why it's efficient or much simpler to work in the Fourier transform or the STFT. Okay? Now, if we work with, if the MTF approximation is not good, when the impulse response is much longer reverberation, in a room like this, the reverberation can be like a few hundred milliseconds. And then then we can work with the CTF, convolutive transfer function approximation. So we choose along each frequency a certain number of windows. Let's call it L prime, L prime windows. And we have frequencies, which is the same, M frequencies. No, sorry. M is the number of sensors, okay? So for each frequency. So we have L prime windows along, for each frequency, L prime windows. And then we have M sensors. So the length of the measurement for each, the number of samples that we take for each frequency will be ML prime. And L prime is much smaller than L here. Why? Because here L is relative or proportional to the length of what we need, the length of the filters. And the length of the filters should be at least the length of the impulse response, or sometimes we can use shorter length because we work with relative transfer functions or relative impulse responses. But L here is long. But if L here is long, as we choose a certain length, L prime is roughly L divided by the jumps or the hops between different windows of the STFT. Okay? So for example, if we take STFT with 50% overlap, so we divide L by L divided by 2. Okay? So it will be 2. If we take overlap of 75%, so it will be L divided by 4, which will, so you see the number of windows L is roughly very small. Another thing, we need to take back windows. So it's not sufficient to take 4. So we need to take, because it will be non-causal, we have to take because of the overlap. So usually we take 1.5 times of this one. So we multiply it. We take at least something like that, 1.5 times of L depending on the overlap. So if the overlap is 75%, we take 1.5 times of this. So usually we take something, if the overlap between windows in the STFT is like 75%, which is a common practice to take 75% or 50%. So we take like 6 windows here. So the length of the vector of measurements that we take, that we process, is about 6 multiplied with M, the number of sensors. And also, you see here, tau, it doesn't start from 0. It can start from -1, -2. depending on the overlap. So with 75% overlap, sometimes we start with tau minus 2. So it can be from minus 2 to 4. So pay attention to these important details when you implement or you work with a problem and you want to implement it in the STFT domain. This is very, very important. How you choose, how you define the problem. Okay, so we took this problem of finding filters of length ML. So here it's L problems of finding filters of length M. Here it's L problems of finding filters of size of length ML prime. But L prime is small, so it's not a big problem. And actually, if L is large, suppose that L is let's give an example. Suppose that L, it's like maybe 100, maybe even more. And we work with 10 sensors. Okay, so suppose that L is 100 and M equals to 10 sensors. So here, the length of the filters is 1,000. So we work with matrices, correlation matrices, 1,000 by 1,000, which is large. And it can be even larger if L increases, if we take here something else. So here, we solve 100 smaller problems. So we find 100 filters of length 10. And we work with correlation matrices of size 10 by 10. It's a huge advantage. Here, suppose that L prime is 6, even with this approximation, the CTF. So we will work with 6 by M, okay, so 60, which is still large, but it enables us to work with smaller problems, okay? Especially if L is large. Maybe it can be even 1,000. Think about it. Even if it's thousands, here still we work with matrices of filters to find filters of length 60. Instead of here, like 1,000 by 10, so 10,000, which is very large filters, very large correlation matrices, so on. So that's why we have a big advantage of working in the STFT, but we need to make sure that we can work with the MTF. If the MTF approximation is inaccurate, you need to extend it to CTF, and then it's a little bit more complicated, but it's important. And this is very useful in many problems, that the MTF approximation is not doing sufficient work. Any question? So this is a comment when we talked about the practical implementation. Now, so we go back to the frequency domain, okay? And because this is much simpler way to work, because you see when we extend here, actually, so it looks like that we need to define a vector of ML prime. It's very similar to the way we work in the time domain, but we do it for each frequency separately. Okay? So the methods that we worked in the time domain, we can use it in the STFT domain. So we combine the methods of the frequency domain and the methods in the time domains when we work with the CTF approximation. This is the convolutive transfer function model. Okay? If you want material, I can give you very nice papers that talk about linear models in the time frequency in the STFT domain, and they talk about MTF approximation and CTF approximation. Okay? There are very nice papers. If you like to read about it, I can provide to you. Okay. Now, we talked about the differences between signal enhancement and beamforming. Okay, so what does it mean? I talk about the main difference when you try to do signal enhancement compared to beamforming. So first, the most important difference that with signal enhancement, you assume that you can estimate or you know the relative transfer function or the relative impulse responses, the same. Okay? So what does it mean? It means that our model looks like this. Y MF is written by the desired signal in the reference sensor multiplied with some value. And this value is the correlation between x1 and xm. Okay, like this. This is the partially normalized correlation. We defined it, okay? So we have here plus noise. Okay. So for signal enhancement, we show that this is actually relative transfer function between xm and x1. Okay, so this is the relative. Actually, this can be written as this equals to gmf divided by g1 f. So if we take x1, we divide by g1, we obtain xf. Multiplied by gm, we get xm. So it's like this, see? But we assume that this relative transfer function, we can estimate, we can obtain it some way. And then, because we have this information, we can estimate the desired signal in the reference sensor. So we can obtain an estimate, which is an estimate of the desired signal for frequency f in the reference sensor, using this vector of measurements, a vector of length m. So we can find a filter of length m that we apply to the m measurement for frequency f, m measurements that are obtained from the m sensors, and we apply the filter to these m measurements, and we get an estimate of the desired signal. This is signal enhancement. So we need to know information about these relative transfer functions and the correlation matrix of the noise. For each frequency, we work with each frequency. Okay, we're done. So here we work with each frequency. And of course, you can do that STFT, MTF, or CTF. Okay, but I'm not going to work further with this approximation because the extension is quite straightforward. You are familiar with the time domain and frequency domain, so you can extend it to any model that you choose. Now, beamforming, the difference with beamforming is that we don't work with relative transfer function. We work with directions. So either you are in environment without any reflections, or you are in environment with reflections, impulse responses and transfer functions, but you assume that you don't know anything about the impulse responses or the transfer functions. You don't try to estimate them. You work with directions. So with beamforming, the model will be y mf equals to x1 f multiplied with, like, instead of relative transfer function, we take the value of the direction, okay? So it can be written like this, d f cosine theta d. So theta d will be the direction of the desired source, and this will be something similar to relative transfer function when we don't have reflections. So it's just exponent. It's actually, it corresponds to delay. See, because if you have a sensor delay when you transform into the frequency domain, so it's just phase difference. Because if you have a signal, a source that propagates and hits or propagates to a sensor array, and this is the observed signal, the desired signal in the reference sensor. So the desired signal in reference number m will be just delay, either plus or minus, so depending if it's before, if it hits that m sensor before or after. Okay? So delay in the frequency domain is just phase difference plus noise. So this is beamforming problem. This is the only difference between beamforming and signal enhancement. Now, okay, so this is signal enhancement, and it's multi-channel, okay? And this is beamforming. Okay, signal enhancement. Let me delete here. So signal enhancement. So we find a filter that is multiplied with the m measurements for each frequency. So this is called filter, okay, or so this is the filter that we try to estimate, the desired signal, using these noisy measurements. Here, also, we can say that we try to find z, but also I will talk what is z, okay? Just a minute. And we apply a beamformer to the vector of measurements. So here we call it filter, here we call it beamformer. Why? Because here we know we apply it to a direction, because we want that the signal that comes from a certain direction will be, for example, undistorted. So here we need to apply requirement that if h is applied to the steering vector, if h is applied, the beamformer is applied to the steering vector like this, vector d f. By the way, here you need to add m, okay? So this is the m element of the steering vector. So add here m. So if we apply the beamformer to the steering vector, which contains all the m components here, theta d, it is required that it will be 1, so we have distortionless response of the array towards a certain direction, theta d. This is beamforming. Okay, but you see, it's very similar. So the methods also are similar. Here, we don't necessarily use this constraint unless we want to work with MVDR or LCMV with distortionless responses. Okay? So we add something similar to that. So H that is applied to the vector of the relative transfer functions, we require that it will be 1 if we want to work with MVDR or LCMV or GSC, just like we saw that it's equivalent. Any questions? Here, signal cancellation happens. Okay. Here, of course, if the signal comes from a certain direction, from theta d, and you keep it without distortion because of this requirement, so the direct path will remain unchanged. Okay? And usually we will get some reduction of the noise. Okay? But suppose that we don't have noise. And we have some reflections from surfaces. So here, we combine, using this filter, we combine the direct path and we combine the reflections into a stronger signal. Here, we suppress the reflections. We don't combine it with the direct path. So here, suppose that we don't have noise. We have less signal in a reverberant environment than we can have here. But of course, if the direct path is the dominant part of the signal, the reflections, let's say that they are insignificant or they are very small. And so, so we have the signal, so we have less signal in this part, okay? But the reduction of the reflections, maybe it's not that significant. And in both cases, we can reduce noise. But it's not the same. Because here we will reduce noise that doesn't come from this direction. So if we don't know what is the noise, we try to reduce noise from all directions, diffuse noise. Here, we can reduce noise that at least if its relative transfer function, if the correlation is different than the correlations in X1. I'll give you an example. Suppose that you have a source, desired source. I have an array here, desired source here, and a noise source in the same direction, but is a different position. Okay? Nice example, right? If we work with beamformer, we direct the beamformer towards the direction of the desired source. We cannot separate them. But here, what we can do is that maybe what we can do is to identify the differences in correlations and then suppress this direction, the direction towards the source, and obtain the source from a reflection. And the reflection of the source with a certain surface is different because it's here. And the noise, maybe it's in the same direction, but it's in a different position, and the reflection will be different. So I'm talking about sources in the room, but it's also possible with radar or something like that. So if the direct path, the direction towards the desired source and the interference is the same, maybe because they are in different positions, the pattern of reflections is different. And here we can distinguish between both of them, and we can separate them. Here with beamformer, we cannot, because we don't take any reflections into account. Okay? This is a big difference, but the methods, once you define the model, we can work with similar methods, okay? Similar methods in the frequency domain or in the STFT domain, because we can work just like we defined yesterday. But beamforming, in general, we have two different methods, or family of methods, two different categories of beamformers. One is fixed, and one is adaptive, okay? And there are differences in these two methods. Okay, with fixed beamforming, let's delete. Okay, so I delete this part, okay? With fixed beamforming, I don't know the environment, which means I don't know the environment, I don't know the relative transfer function, this is beamforming. I don't know the statistics of the signal, so I don't know the variance of the signal in fixed beamforming. I don't know also the information about the noise. I only know that the desired source comes from this direction, and maybe I have undesired interferences from certain directions. So I know only information about directions, the direction of the desired source, and maybe directions of undesired interferences. But I don't know if the noise, what type of noise, what is the statistic, correlation matrices, and so on. So I don't work with these correlation matrices of the noise and the desired source. I don't work with correlation matrices of such. So with fixed beamforming, what I use theta d, okay? Also I use the vector, the steering vector for each frequency theta d. So it's about, I know the direction of the desired source, and maybe I know some directions of interferences, but I don't know what type of noise, so I work either with white performance measures of white noise gain or directivity factor or combination, which means that I assume that the noise is spatially white, or the noise is diffused, or combination. Because I don't make assumptions about the noise. I don't know if what will happen in a practical environment because I design it offline, outside the environment. I don't make assumptions about the environment. So fixed beamforming, the advantage is that it will perform equally for different environments because you don't make assumptions about the environment. It doesn't adapt to the environment. But still, I need to know, or I need to assume that I know the direction of the desired source because I have some steering. I steer the beamformer towards a certain direction. With adaptive beamformer, I assume that I know information not only about the direction, so I assume that I know d f cosine theta d. I also know information, maybe I have information about the signal, the desired source. So sometimes I also know the variance of x1 I know the variance of the desired source in the reference channel. It's very nice information that I can use. I also know the correlation matrix of the noise. Here, the correlation, M by M. So it means that I know a lot of information with adaptive filtering. Actually, I don't know it exactly. I need to estimate. So I need to track, to follow, to do adaptive. In order to do adaptive beamforming, I always estimate. I estimate the direction. I estimate the variance of the desired source in the reference channel. I estimate the correlation. I update these values. I have actually all the time I have updates, updated variables. So I estimate them. Okay. So here, I can try, in this case, I can try to find an estimate of the desired source, actually. So if I actually estimate the desired source using a beamformer that is applied to the noisy measurements, then what's the difference between adaptive beamforming and signal enhancement? What's the difference? What do you think? What's the difference? One difference. What? Exactly. So the difference between adaptive beamforming and signal enhancement is here I assume direction. You see, here I assume a certain direction. Here I assume, or I try to find the relative transfer function. This is the difference. So here I need the correlation matrix. Here I need the correlation matrix phi x, or actually I need the steering vector. Which takes into account not only the direct path, but all the reflections. Okay? So when I track movements of the source, because of the source, I track it. Or I track because of the movement of the array, I need to track the relative transfer functions. And then I call it signal enhancement. But with adaptive beamforming, I only track the direction. And of course, I need to estimate these two. So this is the difference. Now I can tell you, now that you know this difference, ask people who work in array processing if they understand this difference. Okay, ask them, what's the difference between adaptive beamforming and multi-channel signal enhancement? Okay? So it's not that obvious. But now you know the differences between multi-channel signal enhancement, fixed beamforming, and adaptive beamforming. So these differences are very important because sometimes we don't understand, okay, when do we get better performance with this or with this one or with this one? What are the differences? Now things are clear, which is very important. And once things like this, the differences are clear, we can take methods from one to the others. Okay? So we will have 10 minutes break, and then we will see the differences in performance after we understand the differences in the signal model. And what we know, we will talk about differences between these three. Okay? We will talk about differences in performance measures and also differences in the optimal filters or optimal beamformers. Okay? We take a high view of the relations between them. Okay? 10 minutes break, we continue from here. Any questions before we go to break? Yes? Okay, so it depends. Actually, every application that I showed, and you can think, so any application like this, it combines sometimes many things. And sometimes people who design devices, for example, smart glasses, you can think, which methods should I use for smart glasses? Suppose that I want to listen to somebody and enhance its signal. Okay? So here, you will need to estimate the relative transfer functions. But maybe these relative transfer functions are very difficult because if I move my head, these relative transfer functions change significantly. And maybe it's difficult to estimate them in an accurate way. Okay? So suppose that I know the information, everything I know accurately. If I know things accurately, I will use multi-channel signal enhancement because this will provide me the best performance. But when you estimate things that you assume that you know in the model, but in practice you don't know them, you need to include algorithms to estimate them. So for smart glasses, to estimate the relative transfer function, it's very difficult. So you say, no, it's too difficult. I will just estimate or track the direction of the source, like here. But then you think, even estimation of the source direction like this, when I move my head, or maybe that source moves, maybe I don't want to do that. Maybe I will just assume a certain direction, and it will be fixed. Okay? So when I look forward, I will fix like the source is in a certain direction. So if the person moves, I will not hear it, or it will be suppressed. So the person can move his head towards the desired source, which makes sense, right? So maybe I want to use fixed beamformer. But then, fixed beamformer, I need to assume certain noise field. Maybe especially white, maybe diffuse, maybe combination. I don't know the spatial field of the noise field. So do I want to add another algorithm to estimate the variance of the correlation matrix of the noise? If I can afford to add this estimation, it's an additional algorithm. So I will use it. And then it will be adaptive in that sense. But maybe theta, I will use a fixed direction of the source. I will not change it. I will not track it. I will assume a certain direction. So you see, there are many combinations. If I cannot afford, because of complexity, to estimate this, and I cannot afford to estimate the direction of the source, I will use fixed one and certain noise that I think it's reasonable. Some combination of diffuse or some combination or maybe cylindrical noise field. So it depends. Maybe I will have some measurements in different surroundings and I will say, okay, so this is like training data. I will use the same average noise field. Or maybe I can classify the noise field according to some small amount of measurement instead of estimating the correlation matrices. You see, so in practice, when you work on devices, things are more complicated because you need to add, but you need also to understand what kind of information I can use, if I want to add this information, or I would like to make assumptions, and so on. And you have some trade-off between the complexity, so how much information you want to add and estimate, and the error, because when you include additional information, you need to estimate it. And if you don't estimate that information accurately, you add more error. And maybe you know, maybe adding this kind of information which is not accurate, it doesn't improve the performance. So why to try to estimate it? Maybe you don't have time to estimate. You don't have the computational resources or memory and so on. Okay? That's why it makes our life, you know, interesting. If everything, you take the simple things, simple models, and you can solve everything, so we will find another job, you know. Okay? So if you understand this material and you understand what you can do, what are the options, you need to think what is the most beneficial way to solve practical problems. But practical problems are always more interesting. But in order to address practical problems, you need to understand the fundamentals of the methods and the differences. More questions?